Popular culture often frames Nikola Tesla as a solitary eccentric, a man summoning artificial lightning and engineering theatrical sparks in the dark. His engineering was built on precise electromagnetic mathematics and rigorous systems architecture. Tesla approached the physical world through the lens of an architect, constructing the technical foundations that drive global infrastructure today. This animation models the core foundational concept of his work. Here is a single alternating current sine wave. By introducing a second and third wave and timing them to peak at an offset of exactly 120 degrees, we build a polyphase system. When we examine this original patent cross-section of his alternating current motor, we can see exactly how that 120-degree mathematical offset maps directly onto physical mechanical hardware. Understanding his engineering requires mapping this exact physics across his entire career, starting with low-frequency polyphase power grids and scaling all the way up to high-frequency resonant circuits. Tesla's legacy lies in his systematic mastery of the electromagnetic spectrum. To recognize the engineering problem Tesla solved, we have to look at the baseline technology of the late 19th century, the early direct current, or DC, motor. This diagram of a standard DC motor illustrates its fatal physical limitation. To keep the rotor spinning, direct current systems relied on a mechanical commutator, a series of physical brushes that constantly scraped against a spinning cylinder to manually reverse the electrical current. This constant physical friction meant the brushes wore down rapidly. They sparked, they overheated, and they required continuous maintenance, preventing DC technology from scaling up for heavy industrial use. Tesla used alternating current to eliminate the need for these physical current reversing mechanisms. This visual maps the phase offset model. Instead of sending a single current, multiple alternating currents flow through the same system. Because they are staggered, their voltage peaks arrive at different sequential moments. When you map this sequential electrical timing into physical space, the staggered peaks create a continuous, rotating circle of electromagnetic force. Compare this invisible, frictionless rotation to the clunky, sparking commutator of the DC motor. Tesla bypassed a mechanical engineering roadblock by replacing physical parts with geometric mathematics. This schematic of the AC induction motor provides the exact blueprint where the phase offset concept was physically proven. The outer ring consists of stationary coils called the stator. These outer coils receive the staggered polyphase currents we just modeled. As the offset currents fire in sequence, they project a magnetic field that physically rotates around the inside of the housing, entirely without friction. The central component is the rotor, marked here as D. It sits completely unattached inside this rotating field, containing its own closed loops of wire. Through the principle of electromagnetic induction, the rotating magnetic field from the outer stator cuts across the rotor's wires, forcing a secondary electrical current to flow inside them. This newly induced current creates its own magnetic field. The rotor's field magnetically locks with the rotating field of the stator, which drags the solid rotor in a continuous circle. By making the magnetic field do the rotating instead of physical wires, Tesla delivered an infinitely scalable, low-maintenance engine to drive the industrial age. The physics that made the induction motor work at the microscopic level also solved the macroeconomic problem of the power grid. The primary obstacle of the 1890s was transmission. Pushing low-voltage electricity over long copper wires results in massive energy loss through heat. This diagram illustrates the grid logic made possible by alternating current. AC allows transformers to step up the voltage to extreme levels while proportionally dropping the current. Low current minimizes heat friction, saving the energy as it travels over long distances. Once the power reaches point of destination, another transformer steps the voltage back down, making it safe for local distribution and factory motors. The ultimate proving ground for this AC transmission logic was the 1895 Niagara Falls Power Project. This photograph captures the urban density of Buffalo, New York, which became the first major industrial center to run on massive hydroelectric power generated and transmitted from Niagara Falls, 25 miles away. Polyphase AC untethered industry from local geography. Factories no longer needed to be built next to coal plants or rushing rivers. The blueprint for the modern global grid was operating hardware. Having engineered the 60 Hz low-frequency power grid, Tesla pivoted his attention to the opposite end of the spectrum, high-frequency radio waves. This photograph from Tesla's Colorado Springs laboratory captures the device most closely associated with his name, surrounded by enormous electrical discharges. Strip away the theatrical sparks, and the device functions as a dual-tuned air-core resonant transformer. This schematic details the primary LC circuit. It consists of a high-voltage supply transformer, a capacitor to store the charge, and a spark gap. The spark gap acts as a rapid switch. When the voltage breaches the gap, it triggers a violent, high-frequency electrical oscillation through the primary circuit. This brings us to the critical engineering concept of the device: loose coupling between the primary and secondary coils. Unlike a standard power transformer, a Tesla coil has a coupling coefficient of only 0.05 to 0.2. This means only 5 to 20% of the magnetic energy transfers to the secondary circuit at any one time. This deliberate inefficiency is essential. Loose coupling prevents the oscillating energy from rapidly dissipating or snapping back into the primary loop. By trapping the energy, the circuit achieves a high Q factor. The voltage compounds with each cycle, ringing up the electrical pressure until it reaches millions of volts at the top terminal. This photograph of the Wardenclyffe facility shows the ultimate extension of these wireless resonance principles, intended for global communication. The Tesla coil was engineered as an acoustic chamber for the electromagnetic spectrum, a tool built to rigorously manipulate high-frequency energy. The extreme ends of Tesla's engineering portfolio both trace back to a mastery of applied electromagnetism. On the left side of this diagram, his low-frequency polyphase induction motors provided the mechanical muscle to drive heavy industrial manufacturing. On the right, his high-frequency resonant transformers established tuned circuits, laying the groundwork for radio transmission. Together, these form a single, unified architecture. The expansion of the electrical age was driven by mathematical rigor applied to interconnected systems. Global innovation requires engineering these fundamental physical laws. Nikola Tesla moved beyond the individual invention to engineer the essential systems of the modern world.